So if the Gaussian random variables Z1, Z2 are uncorrelated, then the rho Z is equal to 0. If Z1, Z2 are uncorrelated, then rho Z is equal to 0. And 3.63 becomes simply the product of two Gaussian PDFs. Okay, two Gaussian PDFs. If we have the Gaussian random variable Z1, Z2 as uncorrelated, then the rho Z will be equal to 0, and 3.63, which we have written there, right? This quantity will be equal to the quantities which correspond to each one of the ones, separately. F of Z1, this is F of Z1, and this is F of Z2. Okay, F of Z1 and F of Z2 are using 3.65 and 3.66. We have, okay, F of Z1, Z2, Z1, Z2 is equal to F of Z1, Z1 and F of Z2, Z2. Okay, so now, if it's rather very important to consider over here that if the Gaussian random variables Z1, Z2 are uncorrelated, if they are not correlated at all, then the what you call sigma Z will be equal to 0. E of Z1, Z2 will be equal to 0. Covariance of Z1, Z2 will be equal to 0. The covariance, the correlation coefficient, all of them will be equal to 0 if they are uncorrelated. Okay, so in that case, the value which we need to consider will be the 3.63, whatever we have here. So this quantity is equal to 0. So we are left with 1 by 2 pi exponential of, now again, this is equal to the value 0. So we are left with minus Z1 squared. Again, minus of common Z1 squared plus Z2 squared divided by 1 by 2, because this quantity is 0. So we are left with 1 by 2. 1 minus 0 will be 1 itself. 1 minus 0 root will be 1 itself. So 1 by 2 pi exponential of minus Z1 squared plus Z2 squared by 2. And those two terms can be just separated. So if you separate them, we are going to get the quantity which is like this. So what is it we are doing? We are just trying to substitute in the 3.63 the value sigma Z equal to 0. Then I'll get 1 by 2 pi, and this quantity will be 0, and we are left with minus of Z1 squared plus Z2 squared. If I try to separate them out, then it will become minus Z1 squared minus Z2 squared by 2. So two different exponentials I'll get over there. Okay, I can separate it into two different exponentials. Exponential of minus Z1 squared by 2, exponential of minus Z2 squared by 2. And I had 1 by 2 pi there. 1 by 2 pi of this can be divided into two parts, 1 by root 2 pi, 1 by root 2 pi. And that's what is written here. 1 by root 2 pi, 1 by root 2 pi. And each one of this is the PDF of Z1 and PDF of Z2. This is PDF of Z1, this is PDF of Z2. So when they are uncorrelated, then we will have the PDFs to be separated. So in other words, if bivariate random variables are uncorrelated, they are also independent. If bivariate Gaussian random variables are uncorrelated, they are also independent. So this is, rather a very important terminology, which says clearly that if the Gaussian, random variables are uncorrelated, they are also independent. Okay, so this result will lead to, you can extend it to the multidimensional case also. Okay, so multidimensional means f of x1, x2, xn, x1, x2, xn. So n for, if we have, n Gaussian random variables xi, okay, then the joint, okay, so to say PDF of all those is equal to f of x1, x1, f of x2, x2, f of xn, xn. In the case when all those variables are uncorrelated, okay, only when they are uncorrelated we can write like this. Okay, similarly we can try to write the same for the CDF also. This is for the PDF and this is for the CDF. Okay, so and that is only when we have uncorrelated Gaussian random. So these multivariate results for jointly uncorrelated Gaussian random variables turn out to be quite useful in many applications. Okay, so uncorrelated means whenever we have multiple variables, uncorrelated Gaussian random variable will give independent random variables. Okay. So verify either that E of Z1 is equal to 0 or that E of Z2 is equal to 0 as stipulated in 3.68 using the bivariate PDF in 3.63. Okay, 3.68 is what you call written over here. So we need to get mu z is equal to 0 using 3.63. Okay, 3.63. So to do that, we need to consider the what you call equation which corresponds to 3.17. 3.17. E of the 3.17 can be considered from the what you call equation. Okay, do we have that there? I think we have it. Okay, we have it here. Is it? Or in the next one? No, I think we don't have here also. We have it only from 3.46. So we should go to mod 2 lecture 1. Mod 2 lecture 1 will give us that. Mod 2 lecture 1. Bivariate PDF and CDF. So whether we have here 3.17. Okay, so we have here 3.17. fxx is equal to integral of minus infinity to infinity fxy x comma y dy. Okay, so if you want a what you call PDF for single variable, we should try to integrate the what you call the bivariate PDF between minus infinity to infinity once. Okay, so if we take it with respect to this, then we will get over here E of Z1 is equal to minus infinity to infinity Z1. This is 3.17 and 3.17 is here, right? And corresponding to that, we'll get E of Z1 is equal to minus infinity to infinity Z1 minus infinity to infinity f of Z1, Z2, Z1, comma Z2, DZ1, DZ2. Okay, that will give us Z1, FZ1, DZ1. Then using the 3.65, okay, 3.65 is in this itself. 3.65 is here, right? If we substitute it there, if you try to substitute it there, then you will get E of Z1 as the value 1 by 2 pi minus infinity to infinity Z1 e to the power of minus Z1 squared by 2 dZ1, and that will give us the value equal to 0. Okay, so we can take 3.65. So a similar exercise can be done for E of Z2, expectation of Z2, right? Expectation of Z1 is integral minus infinity to infinity Z1 FZ1 dZ1. EZ2 will be integral minus infinity to infinity Z2 FZ2 dZ2. Okay, and again, we can extend it in the same lines. That is FZ1 can be FZ2 can be substituted using the corresponding equations, which can be considered from this place. Okay, so we can consider from the equation which we have considered over here. So if this is Z1, we'll have Z1 here. If it is this Z2, we'll have Z2 here. Okay, so that way we can try to consider it over there and try to substitute over there and get the final result. Okay, so this we can derive very easily when we consider the equation 3.17 and 3.65 and 2.54. 2.54 is the equation which is there somewhere here. This is 2.54, right? E of z is equal to 1 by root of 2 pi integral minus infinity to infinity z minus e to the power of minus z squared by 2 dz, okay, equal to 0, right? Equal to 0. So this is what we have over there, and that is what we have got at this place. Same thing. This itself is the equation which is there here, right? This equation itself is the one which is there here, and that's why it is equal to 0. Okay. So use the equations 3.17 and 3.65 to get the value of this. Similarly, we can use the same set of equations 3.17, 3.64, 2.54 to get E of Z2 equal to 0. Okay. So we'll stop at this and continue in the next class. So just try to check whether we can get the other equations. 32 is the one which is solved here. What are the next equations which we have? Are they similar? If they are similar, we can try to check them. So let me check whether they are similar, and if they are similar at all, we can try to find out. Chapter 3 is this. So